final topic we're going to wrestle with in this section is the idea of a combination. Combinations are very similar to permutations, that you have a distinct number of objects. So they are distinct objects, which means they are unique. None of them are the same. They're all different. A distinct number of objects which the ordered book selected is not important. So the key word here is that it is not important what order they come in. Before, we were looking at permutations, and the order which they came in was important because they would get first place, second place, third place. The order which you put them in would create a different license plate number. You could call a different social security number, a different password into your computer or into your Facebook account, whatever it might be. But the order in which you type these things made a difference. Well, in this case, with combinations, we aren't concerned at all with combination, with the order, because sometimes order just is not going to be significant for us to even count. So the example they give us of the combination is, suppose that you'd select 3 out of 4 books. We used 4 books, A, B, C, D, for a book report, and we chose 3 of those 4 books to use. So we chose books A, B, and C. Now, we use these 4 books in our book report, but the book report A, B, C, if we use these 3 books, our book report doesn't come out different if we chose book A first, then C, then B. That is our second one. Or a third, which is B, A, C. If we use them in that order, we'd still come up with the same book report. And what we're going to see is that there are 5 different arrangements for these 3, or 6 different arrangements for these 3 objects. Because if you think about what was your first selection of your first book, what was the first one that you selected? You could choose from any one of 3 books. And after that, your arrangement is, after I pick my 3 books, I only have my second choice. There's only 2 books left, and after my third, I'm down to just 1 choice left, so I got 3, 2, 1. There are 6 different arrangements for this same combination. So we have 6 arrangements, but they should only count as 1, so what we end up doing is taking our 6 arrangements and dividing them by 6, which only gives you 1 unique combination. And this division by the number of ways you can arrange these objects, there are 6 different ways of arranging the same 3 objects that we divide by. So what you're going to see in our combination calculations is another division creeping in here so that we can get rid of our arrangements. So to find the number of combinations of n objects taken r at a time, so now they're using this language, combination of n objects taken r at a time, divide the number of permutations by the number of ways to arrange each of the selection of r objects. So in order to do a combination, we have n objects chosen r at a time. In our case, we're going to take from 4 books, we're going to choose 3. So we want to be able to take our permutation, which would be of the 4 objects, choose 3, and then divide by the number of ways that you can rearrange those r objects, which is r factorial. The r stands for 3 in our case here, so we want to divide by 3 factorial. And that is what they're getting at here, because if I do a 4 choose 3 factorial, that's going to be a 4 factorial divided by 4 minus 3 factorial all over 3 factorial, which equals, and then we'll do our calculation from there. Okay, so we're going to apply our information in combinations. What you really need to be able to do is distinguish between a permutation and combination. Is the order important, or is the order relatively unimportant? I got a background program I need to cancel here. Give me a second. Okay, so example number 4. How many ways are there to choose 5 cards from a standard deck of 52 playing cards? Okay, so we're going to choose from 52 cards. We only want 5 of those cards. So one of the things we got to do is figure out, when we're playing cards, does it matter what order we get the 5 cards, or do we simply pick up the cards and rearrange them wherever we want? And typically that's how games are played. So this is a combination. We don't care what order we get our cards in. Once we get the cards, we're going to shuffle and move them around anyway. And it's the same hand whether we put one card first, second, third. So the order is not going to make any difference. So it's a combination of 52 choose 5 objects at a time. Now, you could look at it a couple different ways. They said you could do this as a permutation, but then divide by your permutations of how many objects you chose. So in a sense, I'm going to look at this definition and expand it. So really what we're going to do is we're going to take 52 objects, taken 5 at a time. But we don't care what order they're in, so take those 5 objects that we have and get rid of all the orders that they could come in, the 5 cards in that order. So that's our 5 factorial. Well, this permutation of 52 choose 5, that was defined to be 52 factorial all over 52 minus 5 factorial, and then we still have to divide by another 5 factorial to get rid of our arrangements of our 5 cards that we don't care what order they're in. So there's our calculation that we would like to be able to make. So I'm going to use our calculator to help us with this again. So we need to take a 52 and factorial, which is the exclamation point. We want to divide it by, now I'm going to use parentheses in here. Actually, I'm going to do one other calculation here first. 52 minus 5. 52 minus 5 is a 47 factorial times another 5 factorial. So rather than typing 52 minus 5 factorial, I just did this subtraction mentally. So we got 47. Get your math key, get your probability, go down and get your factorial notation key, times, and then I want a 5 factorial. So 5, math, probability, factorial, enter, close my parenthesis, and there should be it's a pretty significant number here yet. I'm not sure where that's first right. 259 8960 and amount 2,598,960 different hands. Okay, so now the other way you can do this, which expedites the whole thing quite a bit, is if you've noticed every time we've gone into this math key and probability, there's another feature that's a combination. So what we want to do is put in our number of cards that we're going to choose from, and then how many we're going to select. So go back to our home screen. We're going to take from our 52 cards that we have to choose from, we're going to go math, we're going to do a probability, we're going to choose a combination. We don't care what order we're getting them in. Choose 5 cards, hit enter, and it does the same calculation for you, but it expedites the whole process, so that's kind of nice about that. Okay. So there's an example of a combination. Let's take a look at another example of a combination. The junior class needs to select a 5-person committee to organize homecoming activities. The junior class is 82 members. How many different committees of 5 are possible? Now, if you got to think a little bit about what a committee is like. A committee is 5 people having the same job responsibilities, the same titles. None of them are more important than the other. We're not selecting one to do one duty or another. We just have 5 people. So because they don't have any distinct title, this is a combination. We've got 82 members of this class to choose from. We're going to do a combination because I don't care what order they come in. I just have to have a 5-person committee, whether that person is Jethro first and Ellie Mae second and Jed third. We don't care. The order doesn't make any difference. So what we're going to run is our calculation of 82 choose 5 on our calculator. So we're going to type in our 82, get our math. Since it's a probability and it's a combination, we're going to choose our NCR, and then you're going to go 5, enter. And now we can record our number, 2728, 5336. Put in my pounds, we got 27,285,336 ways of choosing a 5-person committee from a group of 82 people. I'm going to look at one final example here. From a standard deck of 52 cards, how many ways can you be dealt a full house of 2 aces and 3 kings? So now we got to think about a full house. It says you get a full house, you got to have 2 aces and 3 kings. So we're going to look at our calculating our number of possibilities there. I just got a little interruption. I'll be right back. Okay, there are 2 events here that we're going to be working on. We want to be able to make sure that we get a full house, and event number 1, I'm just going to go E1, we want to get 2 aces. So organize my work. Then I want to make sure a second event happens. My second event that I want to have happen are 3 kings. So I'll just go 3K. This is what I need to have happen. So I don't care what order I get these aces in. I don't care what order I get these kings in. Once I get them in my hand, I'm going to rearrange them 3 of a kind, 2 of a kind, probably so I can see them nicely in my hand. So what we want to do is calculate how many ways I really get 2 aces out of a standard deck of 52 cards. So you got to think about your aces. How many aces are there in a standard deck of cards? Well, in a standard deck of cards, there are 4 aces, and we've got to choose 2 of them. We're going to use a combination because we don't care what order they come in. So that's how, the number of ways we get the event 1 to happen. 4 choose 2. Now we also want to get 3 kings. Again, there are only 4 kings in the deck. Of those 4 kings, we've got to choose 3. If we do this calculation of 4 choose 2 times 4 choose 3, we'll know the number of ways that she can be dealt a hand of 2 aces and 3 kings. So we're going to run our calculations. Clear that to simplify. We got 4 math choose on a combination 2. We're going to multiply it times the number of ways you get the second event to happen, which is going to be 4 math probability. It's a combination. We're going to choose 3. And hit enter, and you only have 24 ways of getting that hand out of the 27 million hands that we calculated earlier. So your probability of this happening is relatively low, and we haven't really talked about how to calculate probability yet, but some of you probably remember it's the number of favorable events over possible events, your sample space. So keep in mind the difference between permutation and combination. Permutation, the order in which they come makes a difference. Combination, the order in which they come doesn't make a difference. So we always divide by the number of objects that we select to reduce our number of orderings of those objects.